All right, are there any questions?
Well, he's gonna turn his lights on.
Did everybody get the homework? I mean, you all have access to it. Did anybody have questions about the homework for us? Any questions? No? Yeah. All right. Set.
Number 2, part.
Pardon?
Number 2, Susie of the homework.
All right. Can you describe it? I don't have my laptop
Oh,
open.
okay.
What does a function look like?
X of t is equal to u of t.
X of t is equal to what?
U of t
Uh-huh.
minus 2 rect t minus 3.
T minus 3?
Yes.
Okay. Is that it?
This part is plot x t minus 2.
What? Say it again. Say.
Plot x t minus 2.
Right, first you have to plot this though.
Right.
All right, so we'll plot this, then we'll take t minus 2 of it. All right, class? So the way I always recommend you do these, if you get more than one function defined here, plot one and then the other and do the mathematical operation. This is my suggestion. You don't have to do it that way. Some people can just see through this. So first I'm going to just plot u of t, and this should be it should be provided in the homework. That should be there. All right, if it's not, let me know. And u of t is simply going to be 0 here. This would be 0, and then it goes to 1 here, and then it stays 1. That's the first function. The second function is the rect function, right? Now rect t, basically, just rect of t itself is going to be what? That's like a pulse function, right? The width, and again, I'm going to say this, when I talk about a pulse function of t, either one's the same, or a rect function of t, it's t over tau. The thing you look at is what is the t divided by, because that says the width. Does everybody see that? Now it's always centered at the point where the argument here is 0. So when you look at the rect function, when is it 0? I mean, when is this argument 0 at t equals 3? So now when I go below here, if I plot minus 2 rect of t minus 3, first thing I'm going to say, I know it's centered at 3. So I know that's where it's centered. Follow me? What's the width? Look what t is divided by. Class? 1, right? The width is 1. That means it's going to go from where? From 2.5 or 2.5, right? To 3.5. That's where the extent is. Sorry if it's a little messy. Now, there's a weight of, I call them weights. It's a coefficient here of minus 2, correct? That means instead of going up to 1, it goes down to minus 2. Follow me? So it looks like this. It's going to be this. It's going to be minus 2. And that's the function. This is rect, minus 2 rect of t minus 3. Does everybody see that? Class? So now you just add them together, point by point. And you can see from 1 to 2.5, it's just 1, isn't it? I'll do it over here. So now when I talk about x of t here, from 0 to 2.5, it's just 1. Then what happens at 2.5, class? To where? Minus 1, right. Now it goes to minus 1. So here it's just going to be constant, then it drops to 1 to minus 1. And it stays there until 3.5. Then what happens? Goes up to 1, right? And it stays there forever. So that's what my x of t is. Do you all agree with that? Now, the next thing was I asked you to plot x of, what was it again?
T minus 2. Yeah, minus 2.
T minus 2. What is that going to do? This is a simple shift. What is it? If that's x of t minus 2 shifts everything over 2 spots, right? 2 times. So now you can take this whole thing. I wish I was a better artist. That's not going to happen. I I take the whole thing and now it's 0, then it goes up to 1, right? Right here. And it stays there for how long? Just add 2 onto that, 4.5. Do you agree, class? Everybody? So it goes up to 3, 4, 4.5, and then it goes down to -1, stays there until 5.5, and then stays there forever. Agree with that, class? How many see this right here? Please give me a show of hands. When I ask this, it's for a reason. I need to know that you see it. If you don't see it, then I need to make sure it's clear. With me? All right. Got that one? Any other questions about the homework? Those are just getting you familiar with the functions, right? And scaling, really, and time shifting. Got a question for you. Just think. If this is x of t, what does x of t plus 3 look like? T plus 3. Anyone? Where does it start? -3. Do you agree? And it shifts this whole thing down to -3. Do you all agree with that?
Yeah.
All right, another question for you. Just listen. What instead of its x of t? X of 2t. Now what happens? Scaling, right? What happens? It squishes it, right? Now, instead of starting at 2.5, it would be half that, right? Or it would be what? 1.25, correct? I mean, I'm sorry. It starts at 0, goes to 1.25, then goes down. And what's the width? Half, right? Then the numbers get a little funny. Then you got fractional numbers. But you all see what I'm saying here, class? Please keep that in mind. This is used all the time in this class. We do scaling, shifting, and you have to be familiar with the functional forms too. Now, I gave you a fair number of them, and I gave you the solutions. I hope you all did them. It's necessary that you do them, so you're right there with me when we start in the next topic. Any other questions about the homework? I don't want to do all the problems, but I'll do, yeah.
This isn't necessarily about the homework, but say your tau was 2 instead of 1 for that rectangle function.
If the width was 2,
Would the -3 also be over 2?
now listen, just listen to me, all right. If say this was rect you're saying it's rect of, I hope you're saying this over 2,
Yeah.
this whole thing right
Would
there?
that -3 be over the 2 or just the t?
Well, the way you have to do this, let me show you this. If you have a function like x of 2t minus 3, the way you always do this is first you break out the scale factor 2, whatever the coefficient of 2 is. We're going to factor that out. So you're going to take this and say it's going to be x of 2 quantity t minus 3 over 2. With me? Now you've got a form you can work with. Listen to me. Now you look at just x of 2t itself and consider that like x1 of t, some new function. Think of it that way, all right? Remember, the x of t here is defined by this view, all right? It's a plot that you have to identify. Now, if you think about a new function, x1 of t, that is really x of 2t, what did we say happens? This whole thing gets halved, right? It's all crunched down, right? Now that is like my x1 of t here. But now when you do the time delay on it, it's not going to be 3, it's going to be 3 halves. Got me? The shift will only be 3 halves, not 3. How many see this right here? And that's why I tell people to think, first scale it, get the coefficient of t, factor it out so you got t by itself. So if you think about x, 2t, I'm not saying it's quite the way I want to, but it's called scaling. You have to make sure the coefficient of t is usually referred to as a in the book. It's the scale factor. Do you understand that, class? You make sure you factor that out and create a new function, if you will. Call it x1 of t like this, which is really x of 2t. Then do the shift here. So then you want to take a look at x1 of t minus, and it would be 3 halves right here. And then plot that. Didn't exactly answer your question. Who asked that?
That answers my question.
It's always going to be scale. First, get the coefficient of t by itself, so you create a function just x of t, x1 of t. Then after that, do the shifting. Understand that, class? The problems are worked out that way, and it should be apparent to you. And in the book, he discusses that. By the way, how many have books now? All right, you all order online or something? Because you're going to need these books. I'm going to tell you, I'll put the problems up and stuff like this, but this book, some of the discussions he has is very good. I don't recommend you use other texts, and I'll tell you why. Certain functions are defined uniquely in here. specifically one called the sync function is different in other books, and he has a unique definition, so please be aware of that. Be careful about accessing the internet and assuming all functional forms. Like when you get sync, I'm just saying this to you, usually it's sine of x over x, but in most signals and systems classes, it's defined as sine of pi x over pi x. In physics, it's really sine, just sine of x over x. How many have heard of the sync function? Surely if you had physics, didn't you remember thin slice diffraction? That was something that the sync function was used to define the actual patterns? No? Do you remember sine x over x functions? Oh, I get heads shaking yes, and never heard of it, man. Pardon me?
I've never heard it called a sync function.
It's called the sync function.
Now for extremely small values of x, it's equal to 1.
What's the erasers?
I see it.
Sometimes.
Oh, they're hidden over here.
Yes.
You want an actual eraser or do you want
Erasers as well.
There's even more over here.
Oh, this will be enough, I hope. All right. Now, what I'm going to do next is first define linear systems. It's not done in this order in the book. Actually, I could do one other thing I'm hesitant to. I'm going to stick with, if I have time at the end, I'll do it. It's not that essential because you've had it already. It's the energy and power definition. All right. Now, the next thing we're going to talk about is what is a linear, time invariant, system. Now, this is what we're talking about. Linear systems, not nonlinear, and they are not time variable systems. So first I have to define what a linear system is. So we can, anything that doesn't fit this isn't a linear system.
Does that say time independent system?
Time invariant. It's time invariant. It doesn't, and I'll get to that in a second. Let me finish this and we'll discuss it. So first of all, what is linear? It says if you have some x of t, I'm going to use the argument t, going into some system, black box is the system right there. We don't know what it is, but it's a system. And you got an output y of t here. A linear system says if I multiply this, whatever this is, by a constant a, I can simply multiply the output by a constant a. Follow me? That's linear. Understand, class? Now, the second thing is, if I add a second function y of t to it, I'm sorry, not y, better not do that. How about, I'll call this, say, I'm going to do this, you're going to hate me for it. I'm going to call that x1, y1. And suppose I add some x2 here of t, then my output would render a y2 of t here. And you can suppress this if you want for a second, but it's saying if I've got x2 of t, it renders y2 of t. Don't worry about how it does that. But now if I go ahead and add the first one to it, it would be additive. And then if I put another coefficient here, b, it simply puts b here. What it means is this, simply put, if I have something, and I'll show you a great example. This is a simple black box. The only operation is that it says the output y is equal to 4x. All right? So here comes my input, and I say I'm going to let x equal 1. All right? My output would be 4. Call it x1. If I put x2 equal 2, my output y2 would be 8. This should make sense to you, right? Now if I added these two up, I would say a third input by the addition of these would be x3 would be 3, and my output here, y3, will just be the addition of these two, or it would be 12. Now, take a look at that. If you just did, I did this by adding these two outputs, right? I knew the output for the first one, the output for the second. I said the output for the sum of the first and the second would be 12 based on addition. But you can also get it by taking 3 times this multiplier, and you in fact get 12, don't you? 3 times 4. So that is linear system. A simple linear system operation. It has no real implied meaning in circuits yet, but that's linear. What's a nonlinear system? This one. Now, for my input, I'll leave the inputs the same, but the operation will now be x squared. All right, whatever the input is, the output's the square. Follow me? So for the first one, I have 1 in, I would get 1 out. Correct, class? The second one, I have 2 going in, I would have 4. Now, if it's a linear system and I added these 2 inputs for 3 going in, I should get 5, right? Right? But what do I get? 9, right. It's a nonlinear system. This is nonlinear. We're not going to be talking about nonlinear systems. The next thing I have to talk about is time invariant. Now, this is something that makes perfect sense to engineers. Time invariant means that if I put, I want to do it here, this is time invariant. If I have an input x of t here, and I get an output y of t, if I delay this, if I take x of t minus tau, then my output simply becomes y of t minus tau. Now that should make perfect sense to you if it's a linear time invariant system. It doesn't matter what the actual time is when the event occurs, the output will always be shifted by that much time. If you shift the input, shift the output. With me on that, class? A good example would be this. If I say my system operation here is y of t is equal to the input x of t plus 3. So that's y of t. So if I put x of t going in, x1, as simply, say, sine t plus, or just sine t. My output, y of t, would be sine t plus 3. If I go ahead and take x, if I take a look at this, just watch me on this. If I shift it and I put x1 here, or now I'm going to shift it, or x2, is equal to sine of t minus 2, my output is just sine t minus 2 plus 3. And if you graph these, the thing is that this tracks this change exactly. Do you follow me on this at all, class? Are you with me? It doesn't matter when you start the event or when you stop the event. Everything shifts accordingly. If you shift the input, you start it 2 seconds later, the output starts 2 seconds later. It's called time invariance. Now, some things aren't time invariant. Can anybody think of anything that depends on the time? Well, this is the most common one I'm thinking of, and it has to do with some of the stuff with NASA. Whenever the sun is radiant on any system, it raises the temperature. Amplifiers are sensitive to large temperature changes. So if you have a satellite circling the Earth, this might not be the best example because they correct for this, but a satellite circling the Earth, if it's on the dark side, it doesn't get any sun radiation and it's cool. And that means the actual transistors, this is a primitive case, are operating at much lower temperatures, so the output for whatever input will be affected. The gain of that system will probably be high at that point, all right, with a low temperature. Now it comes in and the sun's radiant on it, and the temperature goes up. Now the output of that system will be reduced because of the increased temperature on the amplifiers, which means the input-output relationship is a function of the time of day, not just the delay. I mean, you can't delay the signal and you get a delayed output. You follow me on this, class? It's a simple example. That's a system that is now not time invariant. It depends on the time when the input starts and when the output will actually occur. And there's other ways I could explain this, but that was a simple one. Are you with me? So that's linear time invariant systems. That's what we're discussing. And now for the difficult topic. And this is convolution. Please I suggest you start and then you set in your, turn the page in your notebook, or whatever you're taking notes of. This is where it gets rough. This is simple. You can always figure out if a system is linear and time invariant by doing this simple test. Really. And I'll give you some problems with that in it, I think, but honestly, we're not going to be dealing with nonlinear systems, so it's kind of a moot point. It's only linear system. All right, now we start convolution. So write this down. And in my opinion, it's the most difficult topic you're going to face in this course and up to this in your college career. This is my personal opinion, and we're going to do both discrete and continuous time convolution. So what is convolution? First, we're assuming for our sakes, we have a linear time invariant system. So we're going to have some system like so. Please just mark it down as. And I told you before that this system has what's called an impulse response, or an H of t. Now listen carefully to this. We know an impulse function or a delta function looks like this. And when a delta function goes into a linear time invariant system, the system response is defined by H of t. And the output here is simply Y of t is H of t. Now I'll just show you this to give a picture in your mind. Say this is time and this is my delta function I'm trying to show you here, and it looks like this. Normally a delta function is rendered simply by an arrow like that. That's delta t. That's going in. What's coming out? Well, we don't know exactly what it looks like, but for the purposes of discussion, I'm going to say it looks like this. That's my H of t. Are you with me? Now, if it's a linear time invariant system, I'll go over here and do it. If I take the functional input and make a delta of t minus tau into my linear time invariant system, then my output will be H of t minus tau. I'm not going to draw that, but you know it just shifts it, right? It shifts it over. With me, class, on this one? That makes sense to everybody? Now remember, this is a linear time invariant system. The delta function going in gives me an H of t. This is very important. That's called the impulse response of the system. Yes, sir?
So the output is H of t?
Yes, that's the definition. H of t is called the impulse response. It means if an impulse was in, the output would be the impulse response.
Okay,
That's
so
the
it's
output.
same as the function like in the system?
What?
I'm just, because you have the H of t in the box.
That's how the system is defined by H of t. All right, H of t is unique. It defines the actual response of any input. And you're going to see that in a second. But for now, a delta function. Now, follow me on this one, class. Does this make sense to everybody so far? Now I'm going to multiply this by a scale, something. Not a function of t, though. Now I'm going to put x of tau here. Since it's not a function of t, it's like a number, like 5 or 10, right? So now over here, you just multiply this by x. If I gave myself a little more room, a bit easier. Now you can say I can just multiply this by x of tau right here. Are you with me? I just took whatever the input's multiplied by, multiply the output. With me, class? It's tau, not t. It's tau, got it? Now, if I go ahead and say, not only am I going to do this, but something else with linear systems I didn't say, if you have an input x of t and your output is y of t, if you integrate x of t with respect to time from minus infinity to any point in time, dt, you just integrate the output. That should make sense to you. If you take a differential or a derivative of the input, dx dt, you just take a derivative of the output, dy dt. Follow me? That's the only thing you need to do. So what we're going to do here is something where we're going to say, if my input now to a linear system, and this defines convolution, if I take the integral from minus infinity to infinity of x of tau, delta of t minus tau d tau, my output here will be y of t equals to the integral from minus infinity to infinity of x of tau times h of t minus tau d tau. And here's where it gets interesting. Follow me? Do you all agree with that? I'm integrating not with respect to t, but with respect to a dummy variable tau. Are you with me? You can do this. This might seem a little, you're not buying it quite yet. But remember, this system response, h of t, is a function of time, not tau. So effectively, I'm just taking this, and I'm doing a mathematical, I'm just integrating with respect to tau. Are you with me? Now watch this carefully. This is important, this next part. The actual delta function has a very unique property. It can sample the value of anything at the point the delta function, I say, turns on. Now watch this. We know that the integral of a delta function, dt, from minus infinity to infinity is equal to 1. Is it not, class? As an area under the curve of 1. Now, what happens if I had the integral of f of t, delta of t, from minus infinity to infinity, dt? What would that be? What do you think it would be? Let me ask you this. This delta function only exists with a value that's non-zero at t equals 0. Correct, class? Y'all agree with that? So what I'm going to do is say is this. Well, how about if I evaluate this function at 0? Since we know we're going to have the delta function turn on at 0, right? So I'm just going to say it's going to be f of 0 here times the integral really from what? Some minus epsilon to plus epsilon, where epsilon is like 10 to the minus 30th, some value that's ridiculously small, and I have delta of t dt. Wouldn't that be just if I could factor that? Because this thing is going to turn on at 0, I just evaluate f at 0, whatever it is, right? And pull it outside. And then I make the case that this integral here will be 1. So it's simply f of 0. How many see this right here? All right. Do you have a question, someone? Yeah.
What are the bounds of integration?
Very just below and just above 0. 10 to the minus, make it minus 100 if you like. Like 1 over 10 to the 100th power. Just below the 0 and just above 0. I'm trying to, usually in math they say it's infinitesimally small number. Well, we're engineers, and I'm going to give you a real value. Something ridiculously small that no computer would work with. All right? Now, the next thing I'm going to say is this. What would be the value of the integral from minus infinity to infinity of f of t times delta of t minus 2 dt? And tell me why. Think about what we did just a second ago. When does the delta function turn on? When does it go to infinity? At time t equals 2, right? So couldn't I make the case that I could really simply factor out f of 2 and multiply it by the area under the delta function, which is 1? Do you all agree with that? So this is simply equal to f of 2. This is called the sifting property or the sampling property of the delta function. It doesn't matter what's in here. All the coefficients here. You could have 30 different functions. The only thing you need to do is evaluate those functions when the delta function turns on. Got me on that, class? And you have the value of that. So going back to this, what is this equal to? Remember, the integral is not t, it's tau, right? When does this delta function turn on? When tau equals t. In other words, this becomes x of t. Let that sink in for a second. Now I say, for any x of t going in, my output y of t can be gotten by taking the x of, instead of t, tau, replace t with tau, multiplying it by this, h of t minus tau, and integrating the tau, and voila, I get the output. This is abstract, I know it is. But it's true, and it's very important you grasp this. How many see what I've done so far? Give me a show of hands here. Does anybody not? Do you have a question? This is my best shot at, yeah.
I'm kind of confused as to what exactly the delta function is.
Well,
And you explained it yesterday, or on Wednesday.
the delta of t looks like this. Bang, goes to infinity. Has an area of simply 1 under. That means it's going infinitely high and it's infinitesimally small in width, all right? But the product of the height times the width is 1. That's it. It's a mathematical really construct. It's something used in order to solve these things. Do you all see this, class? And this is very important that you do. So now I come here and I say, that's x of t, and well, that's y of t. And this is the definition of convolution right here. This is convolution. But I'm going to tell you a few more things about convolution. The symbol for convolution, and I'll do it over here. We'll get to discrete stuff later, but discrete convolution is something that they really do in real time with computers and stuff to get input-output relationships all the time. So now I'm going to say this. In general, we say y of t is equal to x of t, and the symbol for convolution is the asterisk, convolved with h of t. Now the order doesn't matter. You can say that's equal to the convolution of h of t convolved with x of t. And x and h can be any two functions. They don't have to be input-output. Are you with me on that? Any two functions at all. X of t could be sine of 5t. H of t could be delta of t minus 2. And it doesn't matter which one you put first and which one you put second. And the definition of this one, the first one, is simply the integral of x of tau times h of t minus tau, d tau from minus infinity to infinity. And I'm going to do some of those things because this is where it starts making sense. This is the mathematical definition of convolution, and it's extremely important. It'll become very similar to what's called autocorrelation later. You're going to get that in your next class is random signals and systems. Or a cross correlation, pardon, not auto. Cross correlation. So now, I'll show you the easiest way to do convolution. If you have two functions, and I'm going to come up with two functions that are typical. The first function is going to look like this. My x of t is going to look like this. This is versus t, and this is 1. And my h of t is going to look like this. And this is t, by the way, this way. So now I want to convolve these two functions. I'm looking for the convolution y of t equal to x of t convolved with h of t. And here's the easy way to do it. Remember the definition? I'll put it up here. It says it's equal to, the convolution is equal to the integral of x of tau times h of t minus tau d tau from minus infinity to infinity. But it doesn't matter if you put h of tau here and x of t minus tau. The order that they're there does not matter. Do you follow me? So here's what you always do. You find the function that has the most going on. And you'll notice, first of all, that this integration is with respect to tau. So find the function that's varying the most. This one is varying the most. Do you agree with that? This is just a constant value of 0, right? So that one you don't do, it's called the flip and shift method. That one you graph first, and you do this. You put x or h, but it's going to be, in my case, x of tau here, and it looks like this. And this is going to be tau now. Are you with me, class? Now that's my x of tau right here. Now the next thing you're going to do is graph h, but not of tau, but of minus tau, because you'll see right here, there's an h of minus tau of t0. Do you all see that? So now you graph h of minus tau. Well, what does h of minus tau look like? If that's h of t, if this was tau, this would be h of tau, right? Do you agree, class? What's h of minus tau look like? You just take this and flip it around the axis. It looks like this, doesn't it? Do y'all agree with that? Give me a show of hands if you do so I can see you see it. Can you see it far back? I got to make sure you guys are way back there.
Did you make it like the tau axis?
Yep, that's tau. I'll try to make it clear. Yeah, this is tau right here. It's all going to be tau because the integration is done with respect to tau, isn't it? Class? Now keep watching. Next, what I'm going to do, say right here t is 0. Do you agree with that? What if t was minus 2? Which way would this shift? If you put t minus, let me go ahead and say if I added the t there, but t was minus 2, it would shift this way, wouldn't it? All right, follow me? Right here it's at 0. Now, listen. For time less than 0, these two don't overlap. And I'm just going to show you something. Listen to me now, don't write. If I put t minus tau here, as t becomes negative, this shifts this way. As t becomes positive, it shifts this way. Do you follow me on this, class? So for t less than 0, I know that this times this is 0. There is no overlap of those two windows. How many see that? If you multiply this, since it exists only for negative values, right? Remember, we're really doing a product of the first times the second. So if you take this times 0, it's 0. And 0 times this is 0, right? So the integration of that would be 0. Do you follow me? Now, what I'm going to do is I'm going to let t, and here's where you have to have limits. Now I'm going to say for t greater than 0, but less than 1, this window, this is a visual aid, by the way. What happens is this actually looks like this, where now it's going to stop at t, right? If you think about this, if I have h of t minus tau, and this was my h of t right here, right? H of minus tau was this, right? Now would be h of, I'll put minus tau here, and this is tau. Now as I put this coefficient and let it become more and more positive, this is literally moving in this direction. Do you follow me on this, class? Show of hands if you do. But I limited myself between 0 and 1 because if you think as this thing's moving through here, when all of a sudden it hits 1, right? Now part of it, or greater than 1, is going to be out here, and you would have then 0 times something. Do you follow me? This is going to take some time to really get a handle on it, but you will get a handle on it if you want to. So between 0 and 1, when I take this times this, what does it look like? Well, this is just 1 here, and I chose that for a reason. Because what I'm looking for is the product. This times this, right? So if I take a look at this, if I have 1 times, this function times this function, really what I have is what? I'll go ahead and graph it. If I have x of tau here times h of t minus tau, the product of those two looks like this. And the height is t as well. Remember, that's versus tau. Do you all see that, class? Take a good, careful look. This is hard stuff, and I know. What I'm graphing is this, the product of those two. You all see that, class? Give me a show of hands. How many see that? It's the product of x of tau times h of t minus tau, limited for t between 0 and 1. Understand? Now, I don't want the product, I want the integral, right? From 0 to t. Follow me? I need the area under this curve, don't I, class? I could start at minus infinity, but it's 0, 0, 0, 0, 0. It doesn't matter until I hit 0. And now I need to integrate that. Well, what's the actual equation for this, class? Isn't that just tau between 0 and t? Isn't it just going up at the same rate? Class, how many see this? Y'all see it? Right? It's just a straight line. It's got a slope of 1, right? If it was versus t, the function would be t, right? t. But since it's tau, it's tau. That means what happens when I integrate this? I want to put it down there. I'm going to put it here. Now when I integrate x of tau times h of t minus tau, right, d tau, from 0 to t, I integrate tau. What's the integral of tau? D tau? Tau squared over 2, isn't it, class? Integral of t, or tau, d tau, is tau squared over 2. So now it looks like this. It's going to be tau squared over 2, and that's true from 0 here to 1. So that means the peak value here is going to be 1/2. And this is y of t. That is y of t between 0 and 1. How many see what I'm doing here? I'll do several examples. This is tough, right? This is why engineers are paid so much. You have to be very good at abstract thought and very in hard logic. In other words, you're very good at reasoning and abstraction. All right? That's what pays so much. A lot of people can memorize everything. They're terrible engineers. You have to be good at reasoning and abstraction. Got that, class, everybody? And what am I really doing? I'm doing this operation bit by bit. I put x of tau here, that's this. Then I put h of t minus tau. But the value of t has a lot to do with the value of that integration, right? So between t and 0 and 1, it looks like this. Then I multiply this by this. That's 0 times that is just 0. This has only values up to t, where there's areas overlap. Are you with me? And what you can do is this, because I know this is tough. So you can see between here and here, there's an overlap.
Can you
That-
explain how you got h of t minus tau to look like that?
Yeah, sure, I put h of minus tau here, right? Just minus tau. And then I add t to it. But t, think of a value. When it's 0, it looks like this. If t is what? 1, this whole thing would be shifted over here, wouldn't it? Okay? That's what I'm trying to use this graphical method to help you understand the mathematics.
Okay, so it goes 0 to t then.
Right? Right. 0 to t right here. And that's 0. Well, it's going to go all the way. This should be, let me do it this way. It's going to be at t. You're right. This, I'm sorry about that. I left it like this. This should be, you're absolutely right. I should have done it this way. I should graph this now versus t. And the output here would be t squared over 2 all the way out to 1. So between 0 and 1, this is y of t. Thank you for that. I'm sorry I didn't make that clear. That's right. The output would be t squared over 2 between 0 and 1. With me? Please stay with me on this one. Now,
Why is it 0 to 1 and not 0 to t?
well, it is 0 to t. See, the output's t squared over 2. Any value of t between 0 and 1, the output's t squared over 2. But it's only valid from 0 to 1.
Oh, because the x of t goes 0 to 1, correct?
Well, because the overlap here, think about this. Once I hit 1, all of a sudden this rear part is going to start moving through here, and this part's going to be ahead of that, and I'm going to get to that next. Please just watch this. This is important. So now I'm going to erase this little drawing. I'm going to erase that one too, and start and try to help you. So that's what it looks like between 0 and 1. This is going to be, and I'll just do this. I'll say the output, I know, I'll put it right here. Y of t is equal to t squared over 2 for 0 to t greater than or equal to 1. And y of t is equal to 0 for t less than 0. And now y of t is going to be equal to something else when all of a sudden t is greater than 1. Now when I have h of t minus tau, but now t is going to be greater than 1, but less than 2, what it looks like is this. Now my boxcar here is going to go up to t. Take note, what was the width of this? Look back there. You have h of t, class? It's 1. That means if whatever this number is, you subtract 1 from it. Back here, this is going to be t minus 1. Follow me? The width is maintained. It's very important. You see it? I know. This is where a lot of people change majors. Because they only want smart people in this. I'm telling you. Electrical engineers, chemical engineers, they're probably, in my opinion, the smartest people just about. They might. I'll probably get sued by some physicists, but it's true. Anyway, physicists do this too, so just for the record. Don't change the physics and think you do. So now, remember, t is greater than 1. You'll notice the area of overlap is from where to where? From where to where? T minus 1 to 1, not t. Got it? To 1, right? So now, what does the product of that look like? That's h of t minus tau. Now I have x of tau, right, times h of t minus tau. Now that product looks like this. This is t minus 1, whatever that value is. And then when I hit 1 here, it looks like this, and this height is 1. Isn't it, class? You all see that? Everybody? All right. So what's that area going to be? Isn't it what? it's going to be the integral. Let me do that here. When I go ahead and do this, I want the area under that curve, so what can I say? Y of t, now it's going to be with respect to t, right? We integrate out the tau right here. That's a dummy variable, it's gone. Now y of t is the integral of what? Tau d tau. Remember, this is a function of tau still, right? And this is the product of those two. But really, the product of those two is just tau d tau, right? From where? T minus 1 to 1. Isn't it, class? It starts at t minus 1, correct? And it goes to 1. That's where the area of overlap is. You all see that, class? Give me a show of hands. This is tough stuff, I know it. You're going to spend a weekend scratching your head and thinking about this, but you'll get it. And once you get it, things are easy. But whenever you have areas of uncertainty, you'll get clobbered. I mean, it's not like you miss a few points. I mean, you get 1 out of 10 or 0 out of 10. It's that bad. So just remember that. You have to understand it all, or you almost understand nothing. That's the way convolution is. So now with this one, what happens? Well, that's going to be tau squared over 2, evaluated from t minus 1 to 1. And what is that going to be? Now I have 1/2, right, times quantity t minus 1, right, squared, minus, and, I'm sorry. Let me do it this way. It's going to be 1 squared minus the quantity t minus 1 squared. Y'all agree with me that I left the 1/2 in front? Right? And what is that going to be? Plus, I have 1 minus t squared, right? Minus t squared minus 1, because minus 1 squared. And then I have what? Plus 2t, don't I? Right there, class? Agree with me? And what happens? The 1's go away. And then I get 2t minus t squared over 2. Right? Now, that's y of t for t greater than 1, less than or equal to 2. And what you do is always check this. Right? Now, one thing about convolution, the output will be a continuous function. Let me do one thing over here before I go. Just hang with me for a second, guys. So you see this. Now, when I'm plotting my y of t, I know it's equal to t squared over 2 up to 1, right? Well, t squared over 2 is basically this. And this would have a value of 1/2 of 1. This curve right here is simply t squared over 2. Do y'all agree with that? Show of hands, right? That was the first part. Now between 1 and 2, now it looks like this. Well, first make sure it works. It should be continuous at t equals 1. At t equals 1, I have 2 minus 1, right, or 1, divided by 2, or 1/2. And that value at 1 is 1/2, isn't it, class? So it's continuous. Now what does this look like? Well, this is one of these weird ones. I call it a shark fin. When you plot this, it looks like this. That's what that function looks like. And this is a simple but good example of convolution. And there are a host of them. The thing about convolution I'm going to tell you to focus on, there are always regimes that where the output changes value. Before 0, the output was 0, right? Then what? Whenever the input was between 0 and 1, it's one thing, and between 1 and 2, it's another thing, and between 2 and infinity, it's 0. Got that, class? So you really have 4 regimes where the output is defined differently. Actually, 3. It's either 0, or it's t squared over 2, or it's what? 2t minus t squared over 2, right? And there's a whole lot to this. This is just touching the surface. And this is tough. This is the hardest concept, and we do discrete and continuous time convolution. But here's where engineers, you find out if you're an engineer. Yes. I'll say that. This course, the one following it, random signals and systems, and your digital courses are usually the make or break, especially if you get Nelson, Dr. Nelson, really. Has anybody had him then? Yeah? Yeah, he's extremely good, but he's very challenging. And you've got Dr. New now, a lot of you guys. He's one of the best professors I know of on the planet, and he's challenging too. This concept, though, is abstract. All right, I'm over by 3 minutes. Thank you. I'm going to put some more homework up. Is anybody, hey, I got the link. You sent me the link, didn't you? Somebody? Did you send me one? Hang around for a second, I'll make sure I get this link out. I'll get the video link out if you don't have it. I don't think it is. And I'll put the homework on OneNote. And if you've got questions, bring them up.
There's some middle part where it's kind of maybe, but like,